Good morning. Welcome back to another example with linear transformations. We're going to continue off with the same thing that we did last video on determining if a function is a linear transformation. This time, we'll be working with matrices. So let's get started. So the first one, or I guess the fifth one, we have the function that takes in a 2 by 2 matrix, which hence the M22, and transforms it to just a real number. And so the transformation is the function given the matrix gives you its determinant. So you gotta check if it's a linear transformation. And of course, you could start with the scalar, but I like to do the add. It's usually like the hardest one. So might as well get that one out of the way first. So the addition one. I don't really know how you can do it the traditional way. But what we can do is do both and then check to see if they're equal to each other. What I mean by both, I mean like do T of A plus T of B, which those are matrices. And since this will give you, well, it's a 2 by 2 matrix. So it'll be A, B, C, D. Let that equal, let that equal A, and then let B equal B, C, D, E, F, G, H. Alright, cool. So now we have to find the determinant. So we know the determinant of 2 by 2 is like AD minus BC. So we have AD minus BC plus EH minus GF. Just rearrange those two and just have AD plus EH minus, yes, BC plus GH. So add plus is equal to B minus BC plus GH. All right. Yeah, I don't know what to do here. So we're just gonna stop here and do the other one. So A plus B. And so that would just basically be A plus E, B plus F, C plus G, and D plus H. So we have to find the determinant. And so that would be A plus E multiplied by D plus H minus B plus F multiplied by C plus G. We can distribute, so this would be AD plus A plus Ed plus minus BC minus BG minus FC minus FG. And those two are not the same. So we can see clearly, because they're not equal to each other, it's not a linear transformation. Let's go on the second one. Maybe that one is. So this, I guess the sixth one. The sixth one, again, you were given a 2 by 2 matrix, and it just gives you one real number. And so it's gonna input a matrix, and it's gonna output a sum of all the elements in the matrix. All right, seems doable. So let's do a yeah, TA plus TB. And we know that this is going to be, well, we're going to make it, whatever. We're going to make, we know TA is going to be A plus B plus C plus D. And then B is going to be A, I guess, bar plus B bar plus C bar plus D bar. We can quote unquote combine or group the like terms, even though they're not like. It'll be A plus A bar plus B plus B bar plus C bar plus D plus D bar. And, oh, what do you know? This gives you T of A plus B. So yeah, this is closed under addition, under add. Yeah, 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 because A plus B would just be A plus A bar, C plus C bar, B plus B bar, and D plus D bar. Yeah. So now we're gonna check if it's close under multiplication. So again, we're gonna start with some random constant T, not T, K, A, and so this would be K, A plus B plus C plus D. That is the same as K, A plus whatever, BK, same thing, BK, KB, KC plus KD, which is also the same as the transformation of KA, KB, KC, KD, and we can factor out the K, and we know that this will give us A, B, C, D, which is the same as matrix A. So yes, this is also closed by scalar multiplication. Therefore, that this function is a linear transformation. Woo! Now for the seventh, it's like second to last example. Ooh, I could probably move this up here, because I don't know if I'll need the space. I doesn't want to move. Anyways, so for the seventh example, we are given a, okay, this is not cooperating with me. We're given a linear transformation that goes from a 3x3 matrix to another 3x3 matrix. And so the transformation is, okay, you're useless. There we go. The linear transformation is T of A is equal to a matrix 0, 0, 1, 0, 1, 0, 1, 0, 0 multiplied by that matrix A. Yikes. Sounds like, looks like we gotta do matrix multiplication for 3x3. Woo! Oh, don't you love matrix multiplication? Or do we? Well, let's get started. Let's do the addition one. So, T of A plus T of B. Well, that will give you 0, 0, 1, 1, 0, 1, 0, 1, 0, 0 multiplied by A. Then the same thing, 0, 0, 1, 0, 1, 0, 1, 0, 0 multiplied by B. Well, do we have to do the multiplication? If you want, I mean, that's up to you. But I don't even know if I just talked about this in the past video. But I guess we'll talk about it today. If you recall, I don't know if you did, because I don't. When you do matrix multiplication, there was this property that if we have some matrix C multiplied by A plus C multiplied by B, this is the same as C multiplied by multiplied by A plus B. So what we can do is we can factor out the what do you call it? Oh no, it's about to die. This part, and then add A and B together. 1 0 0 multiplied by A plus B, and whoa, would you look at that? This is pretty much the same as T of A plus B. So yeah, this is close under addition. We like that. We didn't even have to do the multiplication. So I guess like a quick note, when it comes to doing these linear transformations, even as like talking about like real numbers, polynomials, matrices, you got to remember your properties when like adding or multiplying them, because that will dictate if this is a linear transformation or not. And it'll also tell you, yeah, it'll tell you linear transformation or not, because if you do something that is not true, then yeah, you're kind of like, oof. So now let's move on with the multiplication. Scalar version. So let's get K again, and then T of A. And we know T of A is going to be equal to 0 0 1 0 1 0 1 0 0 multiplied by A, because K, that is supposed to be a closed parentheses, not a bracket. Because K is what's that thing called? Scalar. We can multiply with either the matrix that we're given or the one that I was just writing, but we're going to multiply by the matrix that we are given, because this will just basically be TKA, which now shows that this is closed under scalar multiplication. Wow, that's kind of cool. Again, we didn't even have to we didn't have to actually multiply. So that means that this one is a linear transformation. Now let's move on to our last one, the 8th example. So this one takes a 2x2 matrix and goes from a 2x2 matrix to a 2x2 matrix, and it's given the input of any matrix, and its output is a, well, I guess any 2x2 matrix, and its output is its transpose. Cool. Let's do the thing. Let's check it. Do with the addition. So T of A plus T of B, and so that would be A of T plus B of T. So, well, we let A is equal to, whatever. Yeah. A of A is A1, A2, A3, A4. Then let B is equal to B1, B2, B3, B4. That was like a 7. So that's a 4. Trust me. We will get the transpose. If you remember, the diagonals remain the same. It's just the I guess the corners, the ones that change. I guess you could say corners. It's not really corners. The main diagonals stay the same. Everything else changes. So this would be A1, or I guess it flips. A3, A2, A4. Not equals, it's plus. Plus B1, B3, B2, B4. Add those two together because you can add matrices as long as they have the same dimension. Of A1 plus B1, A3 plus B3. I don't remember. A2 plus B2, yeah. Then A4 A4 plus B4? Yeah. And yeah, that's cool. But yo, hello. This is same thing as A1 plus B1, A2 plus B2, A3 plus B3, that's a 3. Okay, that looks less like a 3 now. A4 plus B4. But taking the transpose of it. Whoa. Which means that this is the same as the function t of a plus b. So this is close under, not scalar. This is close under addition. Yo. Cool. So now the last one, which hypothetically should be the easy one. Close under scalar multiplication. So k t of a is equal to k times a of t, which is, we're gonna use the same a. K a1, a3, a2, a4. You can multiply everything inside by k, so ka1, ka3, ka2, ka4, which is the same as the transpose of ka1, ka2, ka3, and ka4, which is the same thing as the function t, ka. So this is also closed under scalar multiplication. So that means this is a linear transformation. QED, the proof is done. Well, we didn't prove it, we just showed it. And that's that's all for this example. That's it for this video of linear transformation. The next one will focus on just finding what the linear transformation gives you given certain conditions or something like that. I don't know how to explain it, but you'll see in the next video. Until then, I'll see you next time.